All right. Hello, everybody. Welcome back. So today, earlier today, we had kind of our lecture on projective schemes and the Proj construction. Um, and so now we are finishing that up because we're doing double sessions until school actually starts. We're going to hopefully finish off chapter 4 today and then get as far as we can into 5 because it's a bunch of definitions. It's not a lot of exercises, and it's like a 10-page chapter. Um, so I would really love to do that. Um, okay, so where we left off was with this bijection existing between prime ideals of this graded ring localized at F, and then at 0, right? So we had this whole business of it being the 0 graded piece of the localization of the graded ring. Well, so prime ideals of the 0 graded piece corresponds to homogeneous prime ideals of the localization of the graded ring. And so the way that we kind of ended was by constructing that. And basically, the kind of confusing part that I don't think we got into was this business of a prime ideal, or showing that the radical of a prime ideal of A0 times its graded ring A radicaled is prime. And I'll be honest, I really don't want to do that. I've been writing RU applications all day, and I am mentally just out of it for doing something that's like a very involved proof. So what I'm gonna do on my own is later tonight, I'm going to go through this, and I'm going to sit with it and work it out. And maybe what I'll do is at the start of the next lecture, I'll walk through my own proof of this bijection existing, and then interpreting the set of prime ideals of the 0 graded ring as a subset of the Proj construction of the Z graded ring. And so, yeah. Kind of the thing that Vakil has right after this is that the correspondence of the points of Proj with homogeneous prime ideals helps us picture Proj. So for example, if our graded ring is over x, y, and z, then we can picture the homogeneous prime ideal z squared minus x squared minus y squared as first a subset of the spectrum of the graded ring, namely a cone, right? And of course, we think of it like this, but this corresponds to a cone. And then kind of taking this affine cone and pushing it to the projective cone, we see that it cuts out something in the infinity ball. And that's just kind of how we're going to think of it. But these, homogeneous prime ideals do this for us. And so this is the geometric picture of what's really happening in projective space. So motivated by the affine case, let T be a set of homogeneous elements, and I'll call these maybe H1 through HR, of the graded ring. The vanishing set of T is the homogeneous prime ideals containing T but not S plus, not the irrelevant ideal. So such that P, or such that T is contained in P, and then P intersect S plus is the zero ideal. And so it is the relevant homogeneous ideals. Homogeneous prime ideals. And that's P. So then it follows naturally that if I is a homogeneous ideal, V of I is well defined. Notice that it is the same as V of T, where T is any homogeneous set of generators of I. Okay, so we can define this for one polynomial at a time in a meaningful way, as long as that polynomial is homogeneous and of positive degree. So note this extends to homogeneous F of positive degree. And that makes sense. 1 over x can't vanish anywhere, so we don't worry about it, right?
Yeah.
Okay, so associated definition. The irrelevant does not vanish, or okay, I guess it's the projective distinguished open is Proj S bullet set minus the vanishing of F. Is the I guess I can't abbreviate that anymore. Projective distinguished open set, which is the complement of V of F. So once we define a scheme structure on Proj S, we will use without comment D plus F, the does not vanish set, to refer to the open subscheme. So D plus F will refer to open, that was not a P, open subscheme, not just subset. And then yeah, although this makes sense for degree 0 polynomials, we deliberately allow only positive degree polynomials. For example, if we want the distinguished open sets to form an affine cover, and if F has degree 0, then basically the distinguished open set needn't be affine. Okay. So I don't know if this is like a remark or what. I'm gonna call it a remark. It's technically an exercise, but Um, so D plus F corresponds to prime ideals of the zero-graded ring that is a subset of Proj, localized at F. So, like, for example, in 4.4.9, in like the first example we gave of projective space, these are the open sets covering the space, like the n+1 affine opens covering the space. Then these are exactly the same thing. And this makes a lot of sense. So the vanishing of F is all of the prime ideals containing F such that, we have this condition here. Well, that's the same thing as being in the zero-graded ring localized at F. Or not in the non-localization of F. But then taking the complement, the distinguished open is the localization at F, and so yeah, they have to correspond. So as in the affine case, the VIs satisfy the axioms of the closed sets of a topology, and we call this the Zariski topology on Proj S. Many statements about the Zariski topology on spec of a ring carry over to this situation with little extra work. Like, I'll add this as a sub remark with D plus F intersect D plus G is equal to D plus F G. And so yeah, in a similar way, the D plus F are a base for the Zariski topology on Proj S. And this is just kind of another fact that transfers over smoothly. Okay, so any questions so far?
No.
So, theorem, let S be graded. So if I is any homogeneous ideal contained within the irrelevant ideal, and if F is in, or if F is a homogeneous element of positive degree, then F vanishes on, the vanishing is the ideal. This can be equivalently written. VI is contained in VF if and only if F to the N is in I for some N. And, this is just very, very clearly little Stellan shots. projective addition. Right? So yeah, and then um yeah. Part two of this theorem is that if Z is contained in Proj S, and we define I of Z to be contained within S plus, then I of Z is a homogeneous ideal of S. Additionally, I of Z1 union Z2 is equal to I of Z1 intersect I of Z2. All of these are classic results about affine varieties and ideals. They just carry over.
Yeah. Okay.
And then finally, for any subset Z contained in Proj S, V of I of Z is Z closure. So all three of these are the projective equivalents of like the kind of major introductory classical results in algebraic geometry. So I don't know, like it seems like they all flow pretty similarly. Two is pretty clearly just a set theory proof. So is three, right? You just show that one is contained within the other is contained within the one. And then for Nullstellan shots, this works the exact same. Like it's proved the same way that you prove the affine Nullstellan shots.
Yeah.
So I don't feel like we need to prove that, but I know I've also been bumping off a lot of the proofs today, because I'm tired, because
Right.
3 hours of sleep. So I don't know. I'm gonna move on for now, but if we get to the end of chapter 4 and I'm like, ooh, we should go back and prove that, we'll come back and prove that.
Okay.
So okay, related theorem. Fix S and a homogeneous ideal I. Then we have V of I is empty if and only if for all Fi homogeneous generating I the union of D plus of Fi is Proj S. And then if and only if the radical ideal of I contains S plus. And I don't need the one. Okay. So let's talk through this. Why does this make sense? Okay, so the variety of the ideal is empty if the functions in the ideal vanish nowhere. Um, and then the homogeneous ideals generating I have non-vanishing sets that are the entire thing. And then the radical is, and this relates up here to this theorem part one, it basically F vanishes on VI is equivalent to VI contained in VF. But if the radical contains the irrelevant ideal, it can't. Specifically focusing in on the second one, because I think 2 implies 1 and 1 implies 2 are the simplest to see. If it doesn't vanish everywhere across all of your homogeneous generating polynomials, then it vanishes nowhere, and vice versa.
Yeah.
Right? So I think this makes a lot of sense, but this is kind of the idea on why this is irrelevant, because it implies not vanishing. And rather S plus has any ideal containing it is geometrically irrelevant. So does this theorem make sense? I know we're not proving it. I know this is more hand wavy than we usually like to do this. But is it at least like flowing smoothly in terms of exposition?
Oh yeah, 100%.
Okay, because I feel like these are all like just perfect analogs of affine space, but with kind of
Yeah.
a unique set of characteristics.
Right.
Um, then yeah, so constructing Proj as a scheme. So so if F in S plus is homogeneous, um, then the non-vanishing is the spec um, of S bullet localized F zero graded to Proj S bullet is an inclusion. Um, admits the property that that Zariski on Proj S restricts to Zariski on spec of the localization of F zero graded. Well, the Zariski topology on Proj S is defined by open sets which are non-vanishings. And so non-vanishings here correspond into, so, okay, so U open in Proj S breaks down into the union of a bunch of irreducible DFIs. And then these actually restrict through our bijection that we didn't prove, but yeah, maybe we should. But they restrict through that bijection to primes of S bullet F0, which in turn correspond back through spec to D plus of F. right? And so open sets go to open sets through the inclusion by restriction to irreducible open components in Proj S. And this makes Proj S like a topological space in terms of how we want to define like the structure sheaf on Proj S as a topological space.
Yeah.
So does that all like glue together nicely?
Yes, it does.
Um, okay, so now that we've defined Proj S bullet as a topological space, we are ready to define the structure sheaf. So on on D plus of F, we want the structure sheaf on spec. Boy, that's getting old. We will glue these sheaves together in the standard way. Um, okay, so theorem, if F and G in the irrelevant ideal are homogeneous and non-zero, there exists an isomorphism between spec S bullet localized F zero graded. Nope, it changed. FG zero graded. Um, and the distinguished open subset uh, um, what? G degree F to the degree G of spec S bullet F localized at zero. Well, we have the standard distinguished open of a graded ring localized here. Zero graded. So then this is the doesn't vanish set. It's no, it's not the doesn't vanish set, but it is. Hmm. So the prime ideals in spec left. Oh, the prime ideals in spec on the left look like the localization of this, and then the zero grading of it is just the underlying field. Hold on, I just want to check something real quick.
Okay.
Um, hmm. Okay, so I'm not crazy. Okay. So this is really just a horrible notation for this. This is spec of S0, and I don't know why I didn't just say that. Um, and so then, yeah. Does that make sense how I'm getting that this is spec of S0, or rather that the stuff
Yeah.
here is just because that was throwing me for a loop. I was like, I think it's that. Is it that?
Yeah.
But it is, so that's good. Okay, so then we're sending prime ideals of the base um, over to non-vanishings of G of some rational thing. So it's all of the spots where G to the degree F doesn't equal 0. Right, like what's the importance of the denominator here?
I have no clue.
Seems like it's not that important. I mean, it's a homogenizing factor clearly, but I don't know. Um, okay. So this is on the right. This is prime ideals not containing. Um, F. Or corresponding to vanishing or not vanishing on the vanishing of F. Still just a little confused on like what the map is. You know, like I can see, okay, these things look like they would correspond, but I can't think of like, okay, let's place a prime ideal on this thing on the left, and let's send it to something that gets sent to. Oh, there it is. Okay, hold on, I have it, I think. Prime ideal not vanishing on FG, which corresponds to DF union DG. And so then this goes over to the does not vanish of, you know, G over F with homogenization contained within the not vanishing on F. And so it happens to be that like the not vanishing on F comes from this union, right? And so the union gives the fact that G is in the numerator to be okay, and that F is in the denominator means that
Yeah.
like we are in explicitly here.
Right.
Um, and so then yeah. So what this looks like practically is S over F to the N, G to the M, getting mapped to nope, never mind.
No.
So okay. Hmm. Hmm. Okay, Math Stack Exchange is doing something weird, and I'm not sure if it's right.
It's usually how it goes with Math Stack Exchange.
Yeah. Let's take a 5 minute break. Think about it.
Okay.
Yeah. Be back at 4:10.
Okay.
Okay, I'm back. So, I guess I'll wait till you're back.
I'm back, sorry.
No, no worries. So I was out there thinking about this for a long time, and I don't get it. And I think that that means that I need to take a nap. Um, but I don't think. So I went and I looked through the rest of the definitions in this section. I don't think we actually need this exercise specifically um, to define Proj fully as a scheme. We just needed to understand Proj as a scheme. And so for that reason, I think that it will be okay if we finish off the rest of these two pages, omitting things that are derivative of this specific theorem. And we come back and we start tomorrow with this.
All right.
And yeah. So it's just, I'm going to have to work through it on my own and just kind of think about it for a little
Yeah.
bit. Right now, I'm just super tired because I got like 3 hours of sleep last night. So
Right.
on the plus side, we got the phone number for security. That's here for a little while. So, if the upstairs
No.
neighbor thing happens again,
Right.
we can just kindly send a noise complaint, and I don't have to go up
Yeah.
and ask them to stop hurling things at the floor. Um, okay. Needless to say, the hand wavy gluing described here is correct. That much I was able to figure it out. Like
Okay.
that is right. I just the fact that I can't write it down mathematically is never a good thing. And so yeah, these gluons behave well on triple overlaps, and that completes the definition of the scheme Proj.
Yeah.
And so we can kind of interpret the structure sheaf of Proj in terms of compatible germs. What agrees on like open subsets and specifically distinguished subsets by factoring through spec. Um, and so this idea of, you know, not vanishing on a function, tying to not vanishing on an ideal, tying to not vanishing on the open subset in Proj as a topology, which then goes to the structure sheaf for gluing these not vanishing sets. That does give us a scheme, and then we can evaluate that in germs, and that works the same way that we wanted it to for affine space. Um, so we will redefine projective space over ring A by Pn of A is proj A over x naught through xn. So here there is no messy gluing or special choice of patches like there was, I think, 2 lectures ago. The x naught through xn are projective coordinates. And it works the way that we've done like computations in the past. It just has this intuition about like non-vanishing and like homogeneous ideals that's more robust but not fully complete. And so the fundamental theorem going on here is that the non-vanishings of each of the xi covers projective n space. And this is a very trivial exercise at this point.
Yeah.
So we started off I think earlier today with a computational exercise about, no, not that one, this one. So about showing that x plus y minus z all squared, that the non-vanishing of that is affine. But with our new perspective, we can show that x squared plus y squared minus z squared contained in P2K is affine, since it is isomorphic to spec of k over x, y, z mod, or no, not mod, localized at the ideal x squared plus y squared minus z squared, and then, oops, and then zero graded, which is the non-vanishing. Right?
Yeah.
And so once we formalize this thing up here, it's all going to make a lot more sense. But the fact that like we understand that these things correspond is enough to say, oh yeah, like we can recognize that that way. It's just sending things back and forth can be a bit painful. Okay, so suppose that K is an algebraically closed field. We know that the closed points of projective n space are in bijection with the points of classical projective space. By this last result here, the scheme projective n space is isomorphic to proj of K over n plus 1 projective coordinates. Therefore, each point of classical projective space corresponds to a homogeneous prime ideal of, well, okay, let me write this out. Each point A naught through AN corresponds to a homogeneous prime ideal of K over X naught through Xn. And of course, that point is X naught minus A naught, X1 minus A1, Xn minus AN. And then homogenized by something, right? So like we're picking over, you know, f to the k over f to the k over f to the k. So we now figure out the right definition of the vanishing scheme, in analogy with the vanishing set. So we will be defining a closed subscheme. So definition, if S is generated in degree 1, meaning that S plus is equal to a bunch of direct sums of S1. It's generated in degree 1. And F in S plus is homogeneous. V of F in Proj S is the vanishing scheme. Well, V of F is spec of S bullet localized at F at 0 And I think that is exactly it, right? No, 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 complement. So then it's proj s bullet minus that, right? And so this is the thing that like completes everything. Does this make sense about like how that ties everything together and how that's like such a big deal?
Yes.
Okay. So, naturally, a scheme which is isomorphic to proj S bullet is a projective scheme. A quasi-projective A scheme is a quasi-compact open subscheme of a projective A scheme. Um, so yeah, a silly example of this is that projective zero space over A is proj A over some variable t, which is isomorphic to just spec A. And so spec A for a ring A is technically, yes, a projective A scheme. It's just a dumb one, right? Or maybe not dumb, silly. A less trivial example is projectivization of a vector space, PV. So we can make this definition of projective space even more choice-free as follows. So let V be an n plus 1 dimensional vector space over K. Here K can be replaced by any ring A and V by a free module as usual. Then we're going to define the symmetric algebra over V as K direct sum V to whatever this V is. Oh, dual. This means dual. V, the dual of V. Wait. Which are the K homomorphisms. Okay, that makes a lot of sense. Wait, hold on, this definition is making less sense. So where VV is hom over the structure sheaf, or I get, no, in this case it is hom over K of V into K. So they're linear functionals. So set linear functionals. So for example, if V is the dual of the vector space with basis x naught through xn, then sim bullet dual of V is k over x naught through xn, and PV is Proj symbolet of the dual of V. In this language, we have an interpretation for the projective coordinates. They're linear functionals on the underlying vector space. So yeah. Okay. I think that that's all I want to talk about now. I could talk about the Grassmannian for a while, but I don't think that that would be very helpful if I talked about the Grassmannian for a while. It's this cool
Yeah.
thing. It's something that I do research with my research for Dr. Field is I work with a Grassmannian, like a lot. But we'll talk about that in chapter 7. So I'm gonna go
Okay.
ahead and stop the recording. And then